This is the story of the development of our understanding of the world of chemistry, from the early days in ancient Greece to the modern view of atomic theory. Around 440 BC, Empedocles suggested that matter consisted of 4 elements: water, earth, air and fire. It seemed logical because when objects catch fire, moisture is released, air can be felt coming up from it, and the ashes show the earth that it contained. Classifying all matter as only being made of 4 elements certainly simplified our view of the world. Around 400 BC, another Greek philosopher, Democritus, also agreed there were 4 elements, but he proposed that there was a limit to how small an element could be divided. For example, if you look at a beach, it looks smooth from a distance, but up close we know it's made up of grains of sand. Democritus said that matter may look smooth and solid, but if we could see it very, very close, then we would see that it's made of pieces. He called these pieces atomos, which means indivisible. He said that the tiny particles were always moving and you could not cut them into smaller pieces. A substance's properties were due to the shape of the atoms. For example, liquids have round particles so they slip over each other, and solids have cubes so that they can stack together easily.
So how big is an atom? It's tiny. Imagine a glass containing 20 ml of water. We know a water molecule consists of 3 atoms, 2 hydrogen and 1 oxygen. Imagine we make each of those atoms as big as a grain of sand and tip the glass of water, now sand, onto the ground. How deep do you think the pile would be? 1 metre? 10 metres? 100 metres deep? The shocking truth is that it would cover the entire continent of Australia to a depth of 3 metres. So atoms are really small. In fact, the diameter is about 10 to the minus 10 metres. Because atoms are so small, we need to have a new unit, and the unit we use is the nanometre, which is equal to 10 to the minus 9 metres. So atoms, therefore, have a diameter of about 0.1 nanometres. Nanoscience is an emerging field of chemistry where materials are manufactured with particles of very small size. At this small size, the properties of the nanoparticles differ from the bulk form because the surface to volume ratio becomes more important. In this example, you can see that if we consider the large cube, the surface area to volume ratio is 2 to 1. But if we look at the small cubes, it is 6 to 1. Since most chemical reactions occur on surfaces, if we increase the surface area relative to the volume, we can make many reactions much easier to perform. This type of nanoscience is being used to deliver medication, to act as catalysts, to speed up reactions, and to help absorb pollutions. There are many more applications of nanoscience which you can read about.
Another Englishman, John Dalton, picked up on Democritus' idea and said that atoms looked like round billiard balls and that each element was made of only one type of atom. These are the actual wooden spheres that Dalton used as models for his atoms. They're about 200 years old. Notice the holes drilled in them. I imagine he used them to connect one to another to make compounds. His models were actually very similar to the ones we buy now to model atoms. Yes, 200 years of technological advancements and our models are not much better. Dalton said that each atom had a unique weight and cannot be created or destroyed. These atoms combine together in simple whole number ratios to form new substances, for example carbon dioxide or in this case ethanoic acid. He tested this by weighing out samples and finding that if he used the right proportions, all the reactants were used up. But if he used too much of one, then there was some left over. This seems obvious to us, but in those days it was not very clear at all. One of his other achievements was to set up an early version of symbols for the elements. However, it was a little too artistic and we don't use it now.
So Dalton said we can have elements which consist of one type of particle which he called atoms, and all of these atoms are the same. These atoms can then combine to form compounds in a fixed ratio in a chemical reaction, and this gives us the variety of the substances that we have on Earth. If we choose to mix elements together, or mix elements and compounds, or even just compounds in a physical manner, we get mixtures, which unlike compounds have no fixed ratio. Chemists soon saw the need to classify and organise these chemical elements to make it easier to understand how they react and perhaps predict how other elements would react. This was first done by Dmitry Mendeleev, a Russian scientist, who organised the elements in increasing atomic mass. He found that similar properties recurred, and so he grouped these elements together into vertical groups. He even left spaces in his table for elements that hadn't been discovered. However, he had to switch some of the elements from this increasing atomic mass order to make the properties fit. This and other evidence led us to our current periodic table. We still have the groups and the periods, but the organisation is dependent not on increasing atomic mass, but by what is happening at the subatomic level.
Name is Thompson. Been working in Cambridge for a few years now in the physics department on cathode rays. Been having a devil of an argument with some chaps in Germany. They think cathode rays are electromagnetic radiation of some kind. I believe they are some sort of particles. Been reading the work of young Dalton on atoms, and I believe he has some good ideas, but I don't believe that atoms are indivisible like he says. I conducted this experiment where I made up a hollow tube with a metal filament and evacuated nearly all the air. And when I passed an electric current through, it glowed green, and a beam of rays, which I called cathode rays, was emitted from the filament. I found that if this beam was passed through an electric field, it was actually deflected. The beam bends towards the positive plate. If I reverse the plates, then the same thing happens. The beam bends towards the positive plate. So I believe that the cathode rays must have a negative charge, and they must have come from the atoms in the filament. Rutherford set up an apparatus which bombarded helium nuclei at a detector. He placed a piece of gold foil in between the emitter and the detector and watched the effect on the alpha particles. Most of the particles passed straight through the foil, which led him to doubt that the charges were squashed into a solid ball of charge as Thomson had proposed. Not only that, occasionally alpha particles were reflected back towards the emitter, which could only happen if they were repelled by another positive charge. So the model he proposed for the atom said that most of the atom was empty space, and that there was a nucleus in the centre of the atom, and this contained a positive charge. The electrons orbited randomly around the nucleus.